So we are in Statistical Rethinking, second edition, chapter 12, and we're on question 12H3 here. And this is dealing with the same data set that was being used in 12H1 and 12H2, namely this hurricanes data set. And in 12H1, we went through and tried to examine the hypothesis that that the number of deaths that are produced by a hurricane was Poisson distributed and was somehow a function of the name of the storm. In particular, the femininity of the name given to that storm. And the hypothesis was roughly that more feminine names produced more deaths in these storms. Now in 12H2, instead of using a Poisson distribution, which is again very limited, we use, or I shouldn't say limited, it's the mean and the variance are set to be equal, and so its ability to fit things that are over dispersed relative to that are limited. And so in the second question, we instead used a gamma Poisson, or otherwise known as a negative binomial model. Okay. And that's what we did there. And now here in 12H3, we are examining a slightly different hypothesis. So not necessarily that feminine named storms produce more deaths, but that there is an interaction between the femininity of the name and somehow maybe the power of the hurricane, and that statistical interaction maybe produces more death. Okay, so here is the question for 12H3. So I suppose I will just read this verbatim. Okay, so in the data, there are two measures of a hurricane's potential cause to death, and those variables are damage norm and min pressure. Okay, so consult the hurricane's data set or data page for their meanings, and so we'll do that here in a second. Actually, let's just do that right now. Okay, so we want to go here. So we have that min pressure is the minimum pressure in a storm, and we're told that a measure of a storm strength, or that lower is stronger. So a lower minimum pressure is a stronger storm. Okay. And then damage norm is the estimate of damage in dollars. Okay. Okay, good. So we've done that. So it makes sense to imagine that femininity of the name matters more when the hurricane itself is deadly. This implies an interaction between femininity and either damage norm or min pressure. So one of these indicators, or one of these indicators of the storm's strength. We want to fit a series of models evaluating these interactions, and then we want to interpret and compare the models. And we're told that maybe using some counterfactual predictions will help clarify this for us. Okay. All right. So we have our data set loaded here. So nothing new here. And we've already looked at what damage norm and min pressure are. So we don't need to do that anymore. Okay. Okay. So to clarify, the hypothesis here is that femininity does matter when the storm is bad enough. Okay. And so maybe this is a little bit plausible. For instance, so maybe when a storm is really bad, people are likely to underestimate what is coming to them if the name of the storm is feminine, right? Maybe thinking that somehow the name is meant to reflect a smaller storm or something like that. And so they don't take the precautions necessary, and worse things happen because the people didn't take the proper precautions. Okay. That's the hypothesis anyway, or it's an explanation to a possible hypothesis. Okay, so we're going to run some models here, and so we have to prepare our data. So it's the same data that we've been using: D for deaths, F for femininity, And then we also have P for pressure, and I'm using B here for damage norm because I've already used D for deaths, and so I just need another letter. And here for pressure, I'm standardizing pressure because I don't really know what to expect. I don't have a sense of what I don't have a sense of what pressure means, or couldn't really even guess what it means in terms of damage or deaths, I should say. And then I'm also standardizing damage here, but I'm using the logarithm of damage because I suspect that that damage is maybe better thought of in terms of orders of magnitude, right? So if I have $100 of damage and $110 of damage, I don't really know that means anything significant. But if I have $100 and $1,000 of damage, an order of magnitude, then maybe that is compelling. Maybe that does tell me something. So, okay. So I'm going to test both of these variables in their own model. Okay, so we have a pressure model here and our damage model here, and they're basically the same. But here, remember, the interesting term here is going to be the interaction between the strength of the storm as given by either pressure or damage and femininity. Okay, so it's going to be this term right here, this interaction between femininity and either pressure or damage. Okay, so here's our model for these things. Okay. I've already ran these, so we don't have to sit here and watch it run. And let's look at the pricey outputs. Okay, so here they are. So let's take them one at a time. What we're really interested here, what we're interested in here is these interaction terms. Okay, BFP and BFB. Okay, so the interaction terms here and here are both pretty reliably positive. Okay, so they're certainly not negative. Okay, for both of these, at least at the 89% credibility interval. Okay, now, but this is a little bit interesting here. So let's look at the bottom one here for damage. I think it's more intuitive to think about. So this is saying that as damage goes up, then so does the number of deaths. Okay, and that should make sense. Okay, but in the second one here, or I guess in the first, where we're using pressure as a surrogate of the storm's strength, it's also positive. But remember that greater pressures signal a weaker storm. So this is saying then that as the storm gets weaker, there are more deaths. Okay, so that seems weird. Now, there's a problem here, which is that these things are on a log scale using a gamma Poisson distribution. And so while I think I'm interpreting these coefficients correctly, I would really like to verify that with some plots. So that's what we're going to do. So we're going to plot we're going to plot predictions for both of these models, and see if we're correct. Okay, and then also examine the interaction terms. Okay, so so I started by extracting samples from the posterior, but it was becoming too burdensome, so I actually don't even need that cell. So here's what I'm using to generate the plot. Okay, so first I've broken down femininity into 3 different categories. Okay, so we have the first third, which is the most masculine names, and then the last third, which is the most feminine names, and then the middle third, which is in between. So so we're going to look at predictions for each one of these levels here. Okay, and now for both pressure and damage, I'm just creating a sequence. Okay, and so we're going to get predictions for each for each value in these different sequences. Okay. Now for the P model, so I have 3 different curves here, so I need 3 different data sets. Okay, one where F is the first category, one where F is the second category, and third, along all values for P in PSeq. Okay, and then I am using the link function to find the expected value of deaths, across the different levels of P for pressure. Then I take then I take the mean of each of these things, right? The mean of lambda 2, mean of lambda 3, okay? And then also look at the credibility intervals. And I think that they're just set to 89%. Okay. And then I do the same thing for damage here, just adapting the code, putting a capital B wherever there was a capital P. Okay. So I think I've ran that. I better make sure. Okay. So let's look at these figures here. Give me a second. Okay, so first we have the minimum pressure one here. Okay, so we have our three curves here, and we'll get to that in a second. But notice that all three curves are kind of following a similar pattern, where at low pressures the depths are highest, and as the pressure gets bigger, the depths go down. And then we see then evidence of our interaction here, because the most feminine names, we see them. So as we go along the x-axis, the most feminine names for the strongest storms seem to predict the lowest amount of deaths, although there's not really a lot of data supporting that. And then as the storm gets stronger, it is predicting more deaths. But again, there's not a lot of storms that are helping, not a lot of data to support that, but that's just the predictions of the model. And so there is the interaction term. Okay. So when we look at this, we see that there's, a lot of the data points are not in any of the prediction intervals. Okay. Yeah, so it doesn't seem to be a very good fit. I think I should actually back up here and say a couple other things here. So notice we have three lines here, right? The blue solid line is for the most masculine. The purple dashed line is for the middle names. And then the pink dotted lines are the feminine, the most feminine names. And then these markers are on a gradient from blue to pink. And so some are going to be purple. And so that gradient, again, is meant to reflect the femininity score of the name. Okay. Okay, so now finally down here to damage. And this model seems to, at least visually, fit the data much, much better than min pressure. So again, this is damage, so the number of damage, or the amount of damage and the number of deaths and how they relate. Okay. And so there does, again, seem to be probably some evidence of an interaction, because as we go along here from least damage to most damage, we see this divergence in the predictions, the damage predictions, okay, or in the death predictions for different levels of femininity. So there does seem to be some evidence of a interaction. But again, notice, well, a couple things that maybe argue against an actual interaction, which is, one, the error bars are pretty heavily overlapping. So there's that. And then secondly, the number of storms that seem to be driving this is really just three storms here. This one, and this one. Maybe this one. But these just happen to have a feminine, or perhaps it is just a coincidence that they have a feminine name with just three storms. That could be a coincidence that they just happen to align with more damaging and destructive or death-causing storms. Maybe this one is also doing it. I think that one looks a little bit purplish. We could examine further, but anyway, there's very few data points that are supporting the conclusion that there's an interaction here, even though statistically there does seem to be some sort of interaction there. Okay. So the final point is, I thought that maybe we should compare all of our models to this point, okay, including the ones that we just did, MP and MB, and it should confirm, what we're seeing here is that MB, the damage, using damage as a predictor, is doing a much better job than using, minimum pressure as a predictor, okay? So I've compared this using WAIC as well as PSIS, and indeed of all of the models that we've used so far, the model we used here, using damage, is the best, and it seems to be pretty far superior to using just pressure as the predictor. So I think the final part of this question asks us if where are we at here? Asks us to determine if the effect sizes are plausible. Um, so maybe we just look at this right here. Um, I don't I don't know what plausible means, but if we just look at how damage is relating to if we look at how damage is relating to deaths here, or it doesn't seem that unreasonable that as we jump up, one standard deviation, two standard deviations up above the average amount of damage, um, that that we are invoking, kind of this very sharp rise in death. So, to my eye, this pattern looks not unreasonable. That maybe from, that we go from very few deaths to now the storm is in a very heavily populated area, um, and causes, one standard deviation more damage, that we have, 25 deaths. And if we went up another standard deviation, that we would expect to see more than a 25% increase in deaths because, well, we have more people there. Okay, so, but to be short about it, I don't really know if these are plausible effect sizes or not.